Deep inside a cryptographic coprocessor, secure computations happen in microseconds. As an algorithm processes a private key, the chip draws power, and that physical power consumption varies slightly depending on the specific ones and zeros moving through the logic gates. If you hook an oscilloscope up to the chip's power supply, you can capture a side-channel attack trace. By using machine learning, attackers can map those minute power fluctuations back to the secret data, recovering cryptographic keys even from heavily protected hardware. But historically, these machine learning attacks run into a severe limitation. An attack trained on one specific hardware implementation completely fails when pointed at a different chip or a different cryptographic algorithm. To target a new defense mechanism, an expert has to manually curate the traces, write custom pre-processing scripts to align the data, and design a bespoke neural network architecture from scratch. It is incredibly labor-intensive. To solve this, researchers developed the Generalized Power Analysis Model, or GPAM. GPAM proves that a single deep learning architecture can automatically recover keys from multiple algorithms, like AES and ECC, and varying hardware countermeasures, directly from raw, unaligned oscilloscope traces. We're going to look under the hood of GPAM and reverse engineer its architecture to see exactly how it maps physical power signatures to mathematical secrets. By removing the need for manual trace alignment and custom model design, this system turns side-channel evaluation from a highly specialized, expensive research project into a fast, scalable testing protocol. The first hurdle GPAM has to overcome is the sheer volume of data. When hardware executes a protected cryptographic algorithm, a single power trace can contain up to 16.7 million distinct sample points. Standard transformer models cannot handle sequences that large. Because the attention mechanism in a transformer calculates relationships between every single point, the computational cost scales quadratically. Processing 16 million points point by point is computationally impossible for standard GPU setups. Borrowing a technique developed for high-resolution images, GPAM applies temporal patchification. Instead of looking at individual samples, the model chops the one-dimensional waveform into contiguous, non-overlapping blocks. To ensure it remembers chronological order, GPAM injects global positional encoding into each patch. Grouping the data this way drastically shrinks the sequence length the neural network has to process, while keeping the vital temporal timeline, the physical inductive bias of the power leak, completely intact. Once the sequence is manageable, the model still has to identify correlations. A piece of cryptographic masking applied early in the execution might interact with a computation millions of data points later. To bridge that gap, GPAM passes the catched sequence into a trunk composed of 3 gated attention unit, or GAU, blocks. GAUs improve on standard transformer encoders by combining the attention mechanism and the feed-forward network into a single gating layer. This allows the model to isolate and process long-range interacting features rapidly, completely bypassing the standard feed-forward bottlenecks. By combining the outputs of these 3 distinct encoder blocks, the trunk flattens a vast, noisy time series capture into a unified, mathematically dense representation of the chip's power signature. The hardest problem GPAM faces is cryptographic masking. To prevent side-channel attacks, secure chips inject random mathematical noise into the sequence, blinding the secret scaler with a random mask so the power signal looks completely decoupled from the actual key. If you point a standard machine learning model at a basic additive masking implementation and ask it to guess the key byte, it achieves an accuracy of about 0.39%, which is exactly random chance. GPAM uses a relational directed acyclic graph. During white box training, intermediate nodes explicitly predict the random mask and blinded secret, feeding outputs into the final target node. This provides the exact mathematical context needed to strip away random noise and infer the true key byte. This chart tracking GPAM validation accuracy proves the model doesn't learn everything at once. First, mask prediction accuracy spikes. Later, the network figures out the blinded nonce. Only then does target key accuracy climb, literally learning to unpack the defense mechanism before reading the secret. A standard neural network fails because it tries to brute force a completely masked cryptographic output. By structuring the output heads as a relational directed graph, GPAM forces the deep network to deconstruct the cryptography step by step. In a real-world scenario, the attack moves out of the white box phase, deploying GPAM against blind raw power traces from a holdout device it has never seen. Against the strongest hardware masks, GPAM won't be able to predict the entire cryptographic sequence perfectly from a single trace, but it doesn't have to. This visualization shows the model's accuracy when targeting just a fragment of the secret. By focusing the network on outputting only the 4 most significant bits of the cryptographic nonce, GPAM uses a confidence metric to rank its best guesses, achieving a 94.8% success rate against additive masking and a 96.3% success rate against multiplicative masking. The attacker extracts these highly confident partial predictions and feeds them directly as inputs into a standard mathematical lattice attack. The deep learning model extracts the signal from the physical hardware, and the geometric mathematics of the lattice attack reconstruct the missing data. Together, they compromise the full secret key using just a few thousand traces. Because GPAM targets the physical reality of the power trace, its architecture generalizes to entirely different algorithms, attacking software-protected AES datasets with 0 structural changes. Adapting this model to evaluate a new chip requires only a few days of automated hyperparameter tuning on standard GPUs, replacing months of expensive manual trace curation by side-channel experts. By automating the pipeline from raw oscilloscope capture to key recovery, generalized models transition side-channel evaluation from a specialized research endeavor into a routine, automated software testing process for the semiconductor industry.